Introduction to Intelligent Experiences. It's kind of like user experiences. And I know half of you probably fell asleep. I'm sorry. User experiences. But this isn't really about user experiences. This is, another way you could think of this is like lecture 2-ish in the Machine Learning Architect series. And that is, how do I put machine learning into a system, including with how it interacts with the user, in a way that helps the machine learning succeed in the short term, but also helps the machine learning get better over the long run. So let's just get into this. I think you'll like it. Right, so you have a model. And what does a model do? A model is not very useful in a user experience, because what's the model going to say? It's going to spit out something like the probability that like song is true given what we know about a user and the history of what they've listened to. Like maybe it's their age and their gender and the songs that they've liked in the past, something along those lines. So you have a probability that they're going to like a song, but what are you going to do? There's a wide range of things you could do with that. You could use it to drive a user experience. So you could say, well, if the probability of liking a song is above something, do something. Well, what are you going to do? You could print the probability on the screen and let the user say, wow, I'm 32.612% likely to like this song. Maybe I should listen to it. But you've never seen anyone do that, right? So did no one ever? So this is just not the right way to think about driving a user experience. There's a translation layer that goes from this raw prediction of the model into interaction with the user that gives the user something that they want, that makes them feel their life was better, but also gives the machine learning process something that it wants and allows it to make the machine learning better. So one thing you could do with the probability that you're going to like a song is you could use it to automate the entire music experience. And that is just take the song that is most likely for the user to like right now, something like that, and play the song. There you go. You sit down at your computer, you open the app, a song starts playing. You really didn't have anything to do with it. It could work, except, maybe you'd start to get bored. Maybe the model's sophisticated enough to realize that, history includes the number of times you've heard this song in the last 7 minutes. But automation is one sort of extreme side of what you could do to connect a machine learning model with the user. Another thing you could do is you could use the machine learning to decide when you want to prompt the user. For example, if the user is doing something on their computer and you notice a particular thing of their behavior and you think they're going to like a certain song, you could pop up a prompt and say, should I play a song or should I play this particular song? You can call me Al. Like, yeah, you could play that on loop forever from me. Well, when I was younger, I listened to that song, let's say a couple of times. So here's a different user experience. The computer doesn't just do something. The computer says, I think you might like to do something. Let me ask you to be sure. But there's other things that you could do. One is you could just use these probabilities to organize the information that you present to the user. There's no decision point. There's just when the user looks at the screen, they see things in an order that better matches how they would, how their preferences might line up. So you could put, don't stop believing, the outfield right there. I can't make that out, and you can call me Al. These might be the top 4 songs that we think you'd like right now. And so they've been organized and your user experience is somehow better because of machine learning. And then another thing that you could do is to annotate the user experience. So this is even less intrusive than any of these others. Is just a few of these, I don't know if you can see that, but a few of these guys have flashing stars on them. So maybe all the songs are laid out the same way for you that they'd be laid out for anyone else, but the ones that the system thinks you might like are somehow sparkly or somehow a little bit more prominent. Well, that's 4 ways that a machine learning algorithm could influence a UI. Let's talk a little bit more about how do you know which of those you should choose, what situations one is better than the other, what are the pros and cons, all that sort of stuff. But before we get there, let's talk about some reasons that intelligent user experiences or connecting models to users is hard. And the first one of these reasons is that there's going to be a lot of mistakes. If you had a model that was 97% accurate, maybe what was your SMS spam model? How accurate did you get that? Let's say you got it into the 97s. I bet you felt pretty good, right? I bet you thought, I'm done. I'm excellent at this. I'm going home. Let the PM ship whatever they want to ship. Tell them to stop bothering me. I'm moving on. But let's imagine that your system has some users, 100,000, whatever, and they each get 3 messages per day. That works out to 9,000 mistakes per day. 97% accuracy, 9,000 mistakes. That's starting to sound like a lot of mistakes, right? Like, how would you like to irritate people 9,000 times? I guess it depends how bad the mistakes are, and this is where the intelligent experience comes in, is you can control how bad the mistakes are. Another way to look at it is 63,000 mistakes per week and 3.2 million mistakes per year. So even a highly accurate machine learning system is gonna do a lot of things wrong. That doesn't mean you can't use it. It just means you need to use it carefully. You need to keep this in mind when you figure out, how am I going to use this model? Other ways you could process this is that each user expects one mistake every 11 days. That sounds pretty good. Sounds like the mistakes wouldn't overwhelm them. But it also sounds kind of lame because every 11 days something just magically goes wrong and the user doesn't really have a mental model for what or why. 30 to 35 mistakes per year, fine. And the question you need to ask yourself is, at what point do those mistakes ruin the utility of the application that you're trying to create, but more particularly the utility of the model, where people around you would say, man, why did we get into this machine learning stuff? It's just not working out, right? So how would you think about that? And in order to understand that, you have to think about each thing that the user bumps into in two different ways. The first way is, what would happen if the user got there because the machine learning model was correct? But on the other hand, you have to look at an experience and say, well, what's the user going to do if they got there because the machine learning model was incorrect? And if the model was correct, you want the user experience to encourage the user strongly to benefit from the model. You would rather automate things than annotate things when your model's correct. The problem is, everything in machine learning is a balancing act, and you don't want to get too much into automation, too much into just making things happen that the user might not want in the case when the model is incorrect. And another big problem with machine learning in general and the types of systems that you need machine learning for is that everything's going to be changing. So on one hand, you might create a new model and the model might be better, 2% better. That means overall on average, out of every 100 things, 2 more are correct. But 2 things got better, but other things possibly got worse. So there could be things that were working before that with this new model aren't going to work anymore. And then you got to ask yourself, what damage will new mistakes cause? Even if overall it's better, new mistakes can impact users in really kind of like ways that make them feel uncomfortable. Like, this phone did something right yesterday and today I can't get it to do it anymore. Like maybe they haven't found the new feature or the new whatever this 2% gain lights up for them, but all they know is something I could do easily yesterday just isn't working. And you got to ask yourself, like, are the mistakes just randomly distributed? So just all across the board, things have got a little bit worse, but really big problems can happen when mistakes are focused on certain users. Like, let's say you do some feature engineering and now all of a sudden everyone with glasses is starting to have a much worse experience. That's not great. And taking that one step further, you could say, well, how costly are the new mistakes? As we said before, the mistake of a false positive is, let's say, worse than the cost of a false negative. And you just have to balance that for your system and say, like, a 2% accuracy, well, how does that map into the actual utility for users who are using the system? And as we talked about with machine learning, you use it for big, open-ended, time-changing problems that are intrinsically hard. And these problems change over time. So a machine learning that was working yesterday, where the user experience was finely tuned and users were getting exactly what they wanted, and then you wait a week or 2 or 3 weeks, it may seem like a bunch of junk to the users, even though, the accuracy for the machine learning on the version of the problem it was trained on hasn't changed, but the problem has changed out from under it. And some specific concerns about that is that models tend to be worse at new things, at things that they haven't seen before. The underlying distribution changed. There's a new relationship between X and Y. The model's not going to know how to do those things. And yet those are the things that might be the most important for users who are interacting with your system. The latency and catching up is another issue. How much data do you need to collect to train for the new concept? If the concept is kind of drifting slowly up and down, you may be able to keep up with some threshold tweaks that might take hours for you to get enough data. But if there are very large changes in what's going on, like COVID, for example, you may have a combination of your machine learning system and your user experience that for a period of weeks, months, something like that is just really, really bad and is not giving users what they want anymore. And you have to make decisions about, well, what knobs do I have? How can I tune things back so that users can continue to use the system and help me build it back up without having the fact that everything has changed make it so miserable for them to use that they give up. And a related thing to having new things come along that the model doesn't know about, Another cost of change is that old things that users used to like and depend upon may have disappeared. And it can be very frustrating for a user who's used to interacting with a device in a certain way. And then, that app or that skill or that, product or something is just plain out of your system. The song dropped from your system, whatever it is. And users can feel kind of unsettled just because of that type of change. And the meaning of a context can change. For example, you might say that news stories that were totally fine 3 months ago are not fine, or jokes that were totally fine 30 years ago are no longer fine. The world's constantly changing, and keeping up is definitely a challenge. And the point of all of this is that there's gonna be a lot of mistakes, and there's gonna be a lot of change, and change can feel like a mistake, even when the change is for the good. So all of this compounds on the user, and you may think in the lab when you're looking at your model, 97% is accurate enough to do a particular thing. You also have to think about, well, if I'm lucky and a user trusts me enough to come back day after day, month after month, week after week, they're going to have all these other pressures on their perception of what's going on in this machine learning system. So we may need to sort of detune our expectations and focus on making sure that the intelligence is presented to them in a very elegant way. And a third set of reasons that creating intelligent user experiences can be hard is you kind of just bundled under this concept of human factors. And I don't know if any of you've heard of this concept of the uncanny valley. Here's a sort of sloppy conceptual chart. And on this axis going up here is the familiarity of a human looking at something or interacting with something. And here is the human likeness. How much does it look like a human? And this chart just says that when something doesn't look like a human, it doesn't feel very familiar to a human at all. And as it increasingly starts looking like a human and behaving like a human, the familiarity can go up and up and up and up and up, but then it hits a point. And this is what's called the uncanny valley here. And the uncanny valley is the place where you're interacting with something that's sort of acting like a human, but it's acting just off. Like something's a little weird. I don't know if you saw Deadwood, the way all the androids there's just something wrong with them. And when you interact with them if those wrongnesses add up to be a little bit too much, it can actually really turn people off. And a great example of that in popular culture recently was poor Tom Hanks did this movie. And I don't think I ever saw it, but it's widely sort of talked about as a movie that the animation was so good that it was terrible. And it's used as an example of what the uncanny valley means, that it exists, and what you feel like when you're in the uncanny valley with a computer experience. And then, of course, once something actually is a human, it feels very familiar to humans that are interacting with it. And this can apply if you're trying to create a complete likeness of a human, but it'll also apply with a user interacting with a system that's supposed to have some smarts behind it. And one way to think of it is the human brain has been trained for a long time to kind of have these two modes of interaction. One is that there's a tool. You pick up a rock, you hit something with a rock. You know what the rock's gonna do. You pick up a soda can, you drink from the soda can. You know what it's gonna do. Versus a relationship where you have to interact with something and it's very subtle and there's a lot of layers to the communication and what's going on. And when you're dealing with a relationship, you don't necessarily expect your partner in the relationship to do what you want to. You hit a rock. It's just like it's a more complicated thing. And I think the human brain gets a little bit stuck between these two places when it's interacting with a computer that's trying to be smart. And the things that you might expect in a relationship where things are more complicated and you don't quite get the action that you want can be very frustrating when you're saying, hey, this is my phone, this is a tool. It's just like, it's a little robot. I should click and it should do. And one reason for this is that with machine learning, you can give it the same inputs and get very different outputs. And now they're not the same inputs, but they may be the same as far as a human can tell. For example, take two pictures and change the brightness on one by 2%. A human probably wouldn't notice the difference. I mean, maybe if you put them side by side, you'd be like, maybe that one's brighter, I don't know. But to a computer going through feature engineering and feature selection and the model and blah, 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 that 2% brightness shift can have a drastic change in what the computer is interpreting. Similarly with like speech recognition, you say a sentence and you feel like you said it exactly the same way you said it before, but you didn't. It sounds very different. Your throat, whatever it is, maybe it's a little dry or whatever. You didn't articulate quite well enough. The computer perceives it completely differently. And the fact that machine learning in general right now is getting there with more advanced perception, but it's not all the way there, can leave people feeling very frustrated, like, yeah. And another aspect of this is that the mistakes that machine learning models make are nothing like human mistakes. Like with a human, if they're trying to do something, maybe they're trying to assemble a shelf and they assemble it a little wrong, you'd be like, yeah, I could see how they got confused by that instruction. I could see where they were going and they didn't quite get there. With a computer, it could do anything. It could make bizarre, crazy mistakes and you're like, no human would make that mistake. And the person who built the machine learning model said, well, this model is 99% accurate and no human is 99% accurate. Yeah, but the 1% of the time it makes a mistake, it is like, woo, like nothing. So the fact that interacting with machines can be very counterintuitive and you feel like you're getting different answers for the same input makes it even harder to work with intelligent experiences. Another aspect is that humans get tired. On the previous slide, we showed like automate, prompt, organize, whatever. Depending on how much attention you demand from your user every time you want to tell them something, they're going to start to get tired and ignore you. So you could ship an intelligent user experience that for the first week, the first 10 times a user interacts with it, they pay a lot of attention and they get a lot of value from it, but eventually they're just like, ugh. And the human brain is fantastic at tuning out things that it's not interested in. And a final thing in this category is that intelligence can be creepy. Machine learning and computers can be really creepy. You know, we're all getting used to these digital assistants that talk back to us. But notice that they all have this very, very explicit trigger word. If they didn't have a trigger word and they just started piping into every conversation when they thought they knew the right answer, that would be creepy. Nobody would like that. So, you know, for all of these reasons, the number one, that there's a lot of mistakes. Number two, that the mistakes change and change, even when it's for the better, can be perceived as mistakes. And number three is just human factors about interacting with machines as they get smarter and smarter and smarter. All of these taken together mean that creating connections between machine learning models and users, it's challenging. It's not really a well understood field yet. All right, so it's not easy, but now you're the machine learning architect or the machine learning program manager or an engineer who's trying to, you want to connect your machine learning model to users. There are going to be a lot of options for how to do it, but what are you trying to accomplish? You're going to lay out three things that you want to think about here. The first is, well, you want to achieve the objectives. Give the user the outcomes that they wanted. Did they get to hear 2 hours of music that they actually enjoyed or not, right? Like, did they get to spend a lot of time interacting with spam in their inbox or not? Did they get to where they were trying to go or not? So these are the outcomes that you need to achieve. And remember, I said you can look at the experience two ways. What happened when the user got there because the model was right, and what happened when the user got there because the model was wrong? Well, you still want to achieve the outcome you want to achieve in either of those cases. So you need to design a user experience that encompasses both of those and gives the user the control that they need without taking the attention that you don't want them to take. And then over time, if you do this, the sort of meta goals are to earn the trust of the user, to get them engaged, and to maybe over time change their behavior so that they come to trust the system more, so that you can move from doing passive things like annotating to doing more active things like automating. And finally, you want to move your leading indicators and the organizational objectives by having a bigger, more engaged user base. Fine. So you got to achieve those things despite the fact that you have a lot of mistakes and things are creepy and it's kind of like human factors and you have to work with your users. The second category of things you need to do is you got to own your mistakes. It's not enough to say like, I'm 97% accurate and 3% of the time my user's stuck. 3% of the time my user's automated car crashes, or 3% of the time I delete all the messages from my user's best friend, mother, whatever it is. And so you need to take control of the mistakes and make them so that they don't ruin the system. The first thing you can think about is to manage the number and types of mistakes the user sees by tuning your thresholds, by controlling what user experience you give to the user in which situation. You can make mistakes more or less costly. Another thing you can do is you can control how easy it is to empower the user, that when you make a mistake, they can, number one, notice it, and that's not too irritating, and it's pretty clear and easy what they could do to correct from or recover from the mistake. And the third category of things is you got to get data to improve the system. And this is very important. Remember when we talked about the first lecture on machine learning architecture, we talked about verifying the system is working as intended, verifying the model quality live matches what you expected it to be in your training environment. And then the third one is get training data from user interactions so you can make your machine learning better. And this is when you can do this if you accept this constraint, and it will be a major constraint on how you design this interaction, but if you accept this constraint and you succeed, getting training data from users can be a gigantic multiplier in terms of getting value out of machine learning cheaply and efficiently. All right, achieving objectives. We're going to go through this in a little more detail, but before I get into it, I just want to make a few points again. The first is that a single machine learning model can achieve totally different outcomes depending on how it's presented to the user, to the point where, and we're going to see an example on the next slide, but to the point where you might perceive it as a totally different product. And as a user, you might think there's no way the same machine learning model is running those two products, but it is. And then a few other points about achieving objectives is that you have to be achieving an objective that's important enough for the user to care. Like you could be doing something that saves the user like 1/10 of a second, but every time there's a mistake, it costs them like 2 hours to undo the problem. And you really have to be like, you know what, I could solve that problem for them, but it's not really worth it. And a couple aspects of that are the long-term fatigue of just having all those interactions and the long-term perception of value. One way to think about it is that if the user doesn't really see when your product is helping them, but the user very clearly sees when your product's making a mistake, that could be bad. And over time, the user might think like, yeah, that thing's not worth it. Like it's doing a 1% optimization to my computer's disk, but when it's wrong, I lose a file. Like, come on, dude, that's not worth it. So let's go through a particular example. And this is a home light automation example. So the model that you have is able to predict the probability that a particular light should be on, let's just say like in your living room, given the current amount of light that's in the room, the lux, that's like higher lux value means that there's more ambient light, whether or not it detected motion, et cetera, like what time of day it is, blah, 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 blah. So you have a model that you can use, and if the model says the probability the light should be on is high, you probably want to turn on a light. So let's say the way we connect this model to the user is through some logic like this. It says, if the probability the light is on is greater than the on threshold, turn the light on. If the probability the light should be on is less than the off threshold, turn the light off. So you can see here you have a couple of operating points that you would need to tune, probably on some validation data, and figure out, I want to control the false positive rate of this particular action and, whatever the problems of that particular action. You could visualize what's going on here, whereas like here's the probability that the model returns on this axis. And you say that if the probability is above that threshold, it's on. If it's below that threshold, it's off. And then if it's in the middle, it doesn't do anything with the light. Okay, fine, great, fantastic. Another thing you might do is you'd say, well, if the probability the light should be on is below the threshold, just turn it off. Otherwise, if the probability the light should be on is below a prompt threshold, prompt the user, hey, should I turn the lights off? Prompt, maybe it's on their watch, maybe the light flashes, the light switch maybe has a little blinker, and maybe it's a voice thing like, hey, turn me off. Hey man, you want to turn me off? And then you could have another threshold where you just warn the user. So you'd say like, look, if you're very certain the light is on, don't do anything, leave it alone. But as you get more and more certain the light should be off, at first you like warn them by flashing a light, then you prompt them by saying, hey man, turn off your light, and then you just automatically shut the light off. That's another approach to it, and you could see that the same model, very different way that the user is going to interact with it. And another thing you could do is something like this, is if the probability the light should be on is below the threshold, start a timer. And if the probability the light should be on is below the threshold for at least 5 minutes, then turn the lights off. Otherwise, reset the timer. And so what this does is like you have a very conservative threshold. It's not just the model dipped for a second below the threshold, but it made a sustained move from above the threshold to below the threshold. And as an aside, when you're running in real-time systems, with a model and you run it every second, the predictions that they make are going to bounce around. They're going to jitter. And this goes back to the point where I said a user might give you what they perceive as exactly the same input, but you give a very different output. So it's often the case that you need to introduce some latency like this into the experience so that things aren't flickering and jittering and bouncing back and forth and making your model look crazy. And then on the other side of this is you'd say, well, if there's any chance the light should be on, turn it on. So there's a very kind of like, this threshold is like a higher value. This is a much lower threshold. Like if it's even 50% likely the light should be on, just turn the thing on, whatever. Okay, so now here's 3 ways of connecting the model to the user. And I left a blank next to each of these objectives. Now, think about those and think about what product would use that logic for connecting the model to the user. Jeopardy time. Boop, 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 boop. Notice I don't want to get, in trouble. So this first one is full automation. I'm shipping a product and I'm like, never touch a light switch again. In fact, rip them out of the wall. Our model is so good, you're not going to need that light switch. Trust us. The second one is to save power. And so what this one is it never turns the light on for you, but it'll start prompting you to turn off the light, and eventually it'll just turn off the light. And then the final one is to keep users safe. So imagine there was an elderly person living in the house, and you're like, look, I don't want them walking through a dark room because they could trip and that could be really bad. So if there's any chance that there's somebody in the room, turn the light on. And not only that, but only turn it off after an extended period of being very certain the light should be off. And in that sense, this system would be the most likely to keep users from getting hurt. You could go measure these things. You could go measure the power usage. You could go measure the number of injuries per person that has this on. You could go measure the number of people sitting in a dark room waving their arms and screaming, turn on, turn on, turn on, with something like this. But there you go. Like I said, the output of a model will tend to jitter around. And so you might look at a time series if you run these models every minute and see some probabilities thing like this. In the full automation case, you can click through this and say, would the light be on or off or on or off? So, it's above the threshold to this point, then it dips below the threshold, turns off for a minute, gets above the threshold, turns on for 3 minutes, dips below the threshold, etc., etc. So this may not be the program you'd exactly like to use. You probably want to avoid these like little 1 minute flicker off by putting some sort of buffer into the UI. In the save power mode, it would be a little bit different. Like, let's say the light starts as on because you were irresponsible and you turned it on and you went out of the room. Well, it would stay on till then it would start flashing the little light on the light switch, which would indicate, hey, if you notice that, turn it off. Or maybe it's flashing on your watch and says, would you like to turn off? You're like, yes or no. That goes on for a while. Then it'll hit the next threshold, which is a more insistent or a more forceful interaction with the user. Maybe that when it calls you on the phone and says, hey, you left your light on, should I turn it off? Something along those lines. And then eventually it turns the light off and the light stays off forever. So what are these forms of interaction? Well, it depends how much you care about saving that amount of power. Like, how accurate you are at getting into this off state, and what's the incremental value of bothering the user for those two communications versus the cost of the power that it's going to save, or how the user, and it could be that there's a lot of users that don't mind getting bothered. They're like, oh, you know what? That phone call would have been irritating in any other situation, but I'm so happy that I'm doing the right thing for the environment that I was happy to take that phone call. And then in the safety one, you'd say maybe the light started as off and then it like crossed the threshold and it turned on. Then it's below the threshold for a while, but it didn't hit the 5-minute buffer. Then it stays on and on and on. And for 1 second, because there was this really long period, it flashes off, but then the light comes back on again and it stays on. And, this is a little better than just whatever, having the light on all the time. But there you go. Anyway, 3 products. You might package them in different boxes and sell them through different sales forces, but they could conceptually all use the same sensors, the same feature engineering, the same machine learning, et cetera, et cetera, et cetera. The second area, achieve objectives, mitigate mistakes. And here's a few things I'm going to talk over quickly, and then we'll get into the example again. The number of mistakes is something you can control, because the number of times your user interacts with the machine learning times the model quality is somehow proportional to the number of mistakes that the user is going to see. So you need to take control of all, you build the model and you do your best, but then you can take control of the number of interactions. That's one step. The second thing is different types of mistakes have different costs. And we'll go through that in a little bit more detail, but you can control the cost of the mistakes that the user is going to have. And the third thing is that users can't recover from mistakes that they don't notice. So think about that. Like, on the one hand, if they don't notice a mistake, they won't blame you. And maybe that's okay. Like, maybe there's, like, I've used this example before, but maybe there's some optimization in your operating system, and every once in a while your computer gets 1% slower, but most of the time it's 5% faster. You don't need to tell the user. There's nothing they can do. They won't know. Don't tell them. On the other hand, if it's something that does damage that the user might want to undo, you got to let them notice the mistake. Otherwise, they'll never undo the damage, and the cost will just be like perpetual, like they paid the cost. And right, you can make it cheaper or expensive to recover from the mistakes. Maybe even build a whole user experience about, this is not junk, add the user to my safe sender list, or undo what you just did, or recover me. Or maybe the mistakes are expensive in that it's like, yeah, call customer support and they'll mail you out a new whatever the machine learning just broke, right? Something along those lines. Okay, so now we've talked about the goals of achieving your objectives, mitigating mistakes, and getting data, but I think we're not covering that here. I think we're going to cover that in a different lecture. Now we're going to talk about some of the tools that you have to help you make the decision of, okay, now I know what I'm trying to do. How can I adapt the user experience in order to achieve that? And you got to think about balancing, it's really like there's these 5 things you want to balance: the forcefulness of the interaction with the user, the frequency of the interaction with the user, the value of success, the cost of failure, and the quality of your model. So when a system is new, when you've shipped your first version of the model, the quality of the intelligence is probably going to be pretty poor. And so there's a couple of things you could think about. Number one, you could think, well, I can't ship it yet. I need to go have better quality, and I'm just going to wait until I get there and then I'll ship the thing. Or you could think, well, maybe I could have a less forceful, less frequent interaction, and I can only go after high value things and provide a lot of structure around mistakes. And one interesting thing about a well-constructed machine learning system is that it will often be worst on the day you ship it at first. And every day after that, it should be getting a little bit better, a little bit better, a little bit better as it gets more users. So you'll often have to think of your experience not just as a like, this is what we're doing, but as this is the life cycle that we're going to go through and how we're going to adapt these things as the quality of the model evolves. Now, if the cost of a mistake is high, you might be like, geez, a surgical robot, what are we going to do? Well, here's one thing you should do. If the cost of a mistake is high, don't automate everything, right? Put a user in the loop. And just because making a mistake is very costly doesn't mean that the machine learning mistake should necessarily lead to a surgery mistake when there's a trained professional also there. And another thing that you might bump into is that you may not have the flexibility to change the UX as much as you like to. Some of these things might be already fixed. And so then you might need to focus more energy on like the value of success or mitigating failures, because you just can't change the forcefulness of frequency because you're working with a legacy system. All right, a lot of things to balance. Now I'm going to go through this terminology and explain it a little bit more. An experience is forceful if it's hard for the user to miss it. So these are the cases where, for whatever reason, the UX gets right up in the user's face. They're not going to miss that it happened. That's a very forceful thing. It's hard for the user to ignore it. So not only don't they miss it, but they can't really not interact with it. For example, a modal dialog box that says, should I launch the nuclear weapons, yes or no? Right? Like, you don't want that to be modeless. So they're kind of like, I don't know, I'll do this other thing for a while and maybe I'll get back to that. No, you can't ignore it. And the final one is that if it takes work for the user to stop it, like launching the missiles in 5, 4, and there's a little cancel, 3, 2, right? Like, so those would be forceful experiences. An experience is passive or less forceful if it's easy for the user to miss. So this would be more like the cases of, I've organized the information a little differently, or I've annotated a few things with a marking that you might notice or you might not notice. And it's okay. You don't need to notice it every time you interact with it, but when you do notice it, it was valuable to you. It's easy for the user to ignore. Same like, those annotations. It's not like, I have to deal with this annotation. No, it's just there. And it takes explicit work for the user to accept it. So the machine isn't automating things. The machine is just kind of like giving the user subtle hints that, hey, maybe you'd want to go in this direction. Maybe you would want to not install that piece of malware. Maybe you would want to, et cetera, et cetera, et cetera. So if you look at those 4 things that I showed at the beginning, the spectrum from automate, prompt, organize to annotate, in general, you could say that they get more forceful as you go from right to left, but the arrows are, so they're more passive as you go from left to right, where the machine just doing something is pretty darn forceful. You might notice it happen. You'll probably notice it happen, but you'd have to go find some button to stop it. A prompt is less forceful, but it's still kind of getting in your face, and it's presenting information to you, particularly if the prompt is big, or like in the anti-abuse case, there's like, are you sure you want to install this file? Yes or no, that type of prompt. Organizing is less forceful. The information may disappear that you might have wanted. So it's still not completely passive because it's changed things. And then the most passive on this screen is that there's a little flashing star on some of these, and maybe you notice them. And of course, like, you could make that flashing star be bigger and then it would be less passive. Or you could make a prompt just pop up a little baby dialogue that users are not likely to see, and then that would be more passive. But just in general, these modes of interaction, this is one way to think about them. And like I said, you would use a more forceful experience when your model quality is high, when the value of success is way greater than the cost of failure, and when training data is valuable. If you want to force your user to have an interaction or force them to experience that mistake so you can learn from it, sometimes that's the right thing to do, and sometimes it's even the right thing to do for the user you do it to in the long run. I mean, users of these systems can actually appreciate what you're doing for them and be like, yeah, okay, sure, whatever, I got a mistake, but I understand that I'm making the system better for everyone else. Now, passive experiences are useful if you're going to be interacting all the time. Like, if there's something you're going to do with a user hundreds of times per day, or like every time they look at their phone, or every time they get in their car, or something along those lines, you might consider maybe this should be passive until we're really, really, really darn sure. And also, you'd want to consider the value of success in that, maybe what you're giving to the user isn't really worth it, and they'd rather just keep doing what they were doing. Okay, so that's one aspect, the forcefulness, and some tools for how you can balance the forcefulness and tune it up or down. And I'm going to give you an example of this being used in practice. You've all had experience with email systems, and here's a little abstract chart. On this axis is forcefulness, and you could see at the highest point right here, it's delete. And on this axis is intelligence quality. So if your intelligence quality, for whatever that means, false positives, false negatives, at your operating point, blah, 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 you might say, well, I'm going to delete the message. And in case you didn't know, spam filtering systems delete a lot of messages, like really, really a lot of messages. So it's happening. It's a very forceful thing to do. You don't know that your friend's email to you got deleted. There's nothing you can do about it. It's just gone. Okay, but if the quality of your intelligence is high enough, that's the perfect spam experience. Because I don't want to look at something in my inbox. I don't want to have a junk folder. I just want it deleted or in my inbox. I want everything to be perfect. But we never quite get there. So we need other experiences layered on top of that delete experience. And the first one that you might think about is that junk folder. And the junk folder, I call it suppress here. And that is, I take a message that the intelligence somewhat thinks might be spam, and instead of deleting it, because that's too forceful, because the intelligence quality isn't good enough, or the message didn't reach the certain threshold, instead we're just going to move it to the junk folder. It's not great. The junk folder is going to have some good mail in it, and the user's going to have to go skim through it anyway, but overall they feel better and they feel empowered to not have their inbox just filled with stuff and there's nothing they could do about it. And then if the quality is not as good or the model itself is not as certain, you might just inform the user. Like, you might put the message in their inbox, but at the top of the message, you'd say, hey, responding to things on the internet could be dangerous, or never give your password to somebody on the internet, or never give your credit card, blah, blah, blah. So that's something that, as the creator of the email system, you can do to inform the user that, I'm not super sure about this message. I don't want to tell you even that I'm not sure. I just want to give you in context some information that might help you be safer, or you might ignore it. I don't know, but at least we've tried. And this is what I don't know. I mean, I worked on spam filtering a long time ago, but at the time, everybody did this. They had all these different layers of experience that were increasingly forceful, depending on how do we maximize the protection that we provide to users without making the protection so onerous that they feel that they're not getting a good deal out of interacting with the mail system and just stop or go somewhere else or whatever it is. All right, number one, forcefulness. Very important. Very important. And you can have multiple tiers of forcefulness within a single application. The second one is frequency. And in general, it's just like, how often do you want to allow the model to interact with the user, or under what circumstances? And as I mentioned before, frequent interactions will fatigue users, and users will start to ignore them. And if they're forceful, frequent actions, users are going to start to get pretty kind of like peeved probably. But infrequent interactions just have fewer opportunities to create value. So you really do want to balance and get the most forceful interaction that you can get away with as frequently as you can get away with showing it without breaking the system and causing it to be a problem. So one approach to frequency would be that whenever a prediction changes, you change what's happening. So if you're automating, you would be like, hey, I think you want to hear You Can Call Me Al now. Nope, you want to hear Don't Stop Believing. Nope, you want to hear that Outfield song. I forget what it was. And just flash back and forth between them. Could be a bit of a disaster. You probably want to hear to the end of a song. This is a bit of a joke, but you know. So every second, you call the model, you update the UI. It's useful for things like real-time control, or where there are extreme changes, or where you have a super high-quality model, and you're just going to be like, let the model do its thing. I don't want to like bother the user to say, hey, we both know the model's right. Click yes again, right? Like, why would you want to do that? Another thing you could do is just wait for significant changes. That is, if the thing that is currently playing, here, let me just click and see what I wrote here. So if the current answer is different and the delta in probability is greater than some threshold, and or the current answer is different from the previous answer for more than n seconds, then make a change. So I don't know if you noticed that this animated and it animated slower than that one. This type of significant change can be useful to reduce the jitter, reduce the fatigue on users, because, you know, like a small delta P, a small change in probability between what's currently there and what you'd like to do, probably would have less value than a large change. So you can do that. And, you know, not every application allows for latency, but when latency is acceptable, you pretty much want to make sure you're doing some kind of like buffering like this so your system doesn't act crazy. The third thing you could think about is to have a buffer for how often you're willing to interact with the user in a particular day. You could be like, man, I'm going to interact with them 10 times today. I want to make sure they're the 10 best interactions that I can pluck. A bit of a like, I'm not sure if I should interact now or if I should wait for later. You come up with some sort of a policy. That might be a good place for reinforcement learning, which we'll talk about in a later lecture. But you could say like no more than n times per session. Like the first n times I cross this threshold, I'm going to do it. Otherwise, I'm not. Or you could be like at most once per minute, once per hour, whatever you want to do. This can be useful when testing your interactions. Like I've just have this throttle so that I only show each user at most one prediction per day, and I see how they interact with it, and then I use that to tune my thresholds or to know if I want to ship the model or not. You can use this as a additional filter to reduce fatigue, and also, like I said, gathering data for testing the interaction, stuff like that. Another thing you could do is explicitly model the user. So it's not just a matter of what does the model think, but what is my estimate that of the probability the user will accept. So maybe I have a different model for each user on what songs, how often they like to change their song. Maybe it's a very simple model, and you know, as long as it's above the X, I do the interaction. And of course, almost always when you have users interacting with a system where there's an intelligence in it, you want to provide a backstop. So if they want to play a song, they don't have to wait for your system to tell them, hey, I'm going to start the song for you. They have to be able to browse through and do the optimization, find the message, start the song, whatever it is. All right, well, let's just go through a quick example: forcefulness, frequency, value, cost of mistakes, and model quality, and just look at one scenario of how they might interact. And this is a break finder. Maybe it's an assistant for a doctor. And here are the various experiences. You show the system the X-ray of a broken bone, and it'll put a little annotation on it and be like, Mr. Doctor, I see as the AI, I see something here. You might want to take a look at it. Not super forceful necessarily, but if the doctor is scanning the X-ray and he can call up the overlay of where does the system think there might be a break, that could be a valuable thing. Another is that you could say, hey, doc, I'm pretty sure there's a break here. Verify that there's not a break. This is a more forceful thing to do. Right, and then the most forceful thing that I have on this array on the system is just that, hey, the system takes in the x-rays and it orders treatments. And at the end of the week, it says, hey, doctor, I treated 47 breaks. And by the way, you wasted 782 x-rays you shouldn't have taken because there was no break there. That's the most forceful of these experiences, because the doctor would have to dig in, go through the records, try to find, oh, which one did they treat, which one didn't they treat, and try to do some serious work to find or correct a mistake. Or the patient goes home with a broken bone and comes back later and says like, hey, my arm still hurts. Are you sure? Are you sure I shouldn't have a cast on this thing? Okay, and so if your model quality is poor, you're pretty much stuck with there. If your model is better than a human, you might want to do that. You could very well probably be better off doing something like that. So now the question is, how do you balance the frequency? And when your model is poor quality and you're doing something that's not too forceful, maybe you want to have a high precision threshold so that when that little thing comes up, it is pretty sure, you don't want to have a lot of mistakes on that or the doctor will just start ignoring it. In this case, you might want to have a high recall threshold so that if the doctor is like, nah, I don't see anything here, the system might say, whoa, 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 are you sure? Are you absolutely sure? Because this might be a break. So you can see how the frequency might be guided by very different things. And this is just run on every single interaction. And here the value is also on a spectrum. And on this top case, the doctor might spend a little less time per scan, maybe a few seconds, because they have that backstop. When you're prompting, that could be great training data, because now you can say, well, my system thinks something's here, and then you can get a doctor to provide a label. So often one of the reasons that you want to do prompts, even though it's kind of like awkward, is that it gives very, very clear labels for specific cases that you care about. And then, as you get further down, you might just triage out or automate things. And if the intelligence is better than humans, you're going to have fewer mistakes overall. So the value could be quite good. Looking at the cost side, the doctor could become too reliant and stop looking for breaks on their own. And the model quality is poor, but the doctor comes to rely on that poor model. Another thing that could happen is that the doctor just totally ignores it. Is like, no, it's poor. I'm not going to use it at all, even though it could have helped them. Patients untreated or overtreated, depending on where you prompt. If the doctor becomes reliant on the prompt and the prompt is missing systematically certain types of breaks, that could be a bad thing. And then if the hospital just hands everything over to a robot, maybe it gets sued, God knows, whatever. But just a quick example showing you could make a matrix like this for your application, and you could run different scenarios and ask yourself, well, what is the right way to balance this user experience, given the quality of my model, given what the application needs to achieve, given where I think I'm going? All right, we made it. A little bit kind of like UXC, hand wavy, blah, blah, blah. But I do really think it's important for you to hear that, to think through it, stretch your brain a little bit, because when you're building the model, knowing how it's going to be used downstream, these types of problems that the people who are going to pick up your work product and try to turn it into value are going to face, well, it'll just make you better at your job, make you more empathetic. So for the summary, the goals of the intelligent experience are to take the predictions from the model and present them to the user in a way that achieves the user's goals and achieves your goals, achieves the objectives. So that means you have to prod where you're right and back down where you're wrong, because you need to minimize the flaws. You don't want the flaws to overwhelm the potential value, so that both you and your users are like, rip this thing out, man. I don't want this intelligence in here. And a very, very important pattern for machine learning is closing the loop. We talked about it briefly about, presenting prompts, presenting interactions in a way where when a user ignores it, when a user interacts with it, you can say, aha, I have a label now that I didn't have before. This is fantastic. Now, intelligent user experiences are hard because of mistakes. Machine learning always makes mistakes. You're going to make mistakes. There's nothing to do about it. Embrace them and mitigate them. Don't complain about them. Don't be defensive about them. Change and human factors are other reasons that setting up these interactions can be quite difficult. And when you're doing an intelligent user experience, you have to think of balancing 5 things. And it's a lot to think about. There's so many different factors, and you'd be like, well, how do I get all 5 in balance? But don't think about it that way. You don't have to think about it that way. You could think of it as, I have 5 levers I can pull to help make my machine learning more effective, to ship my machine learning sooner than I would have been able to without the ability to control these 5 levers and to get the machine learning live in the marketplace faster so I can start to get feedback and so I can start to do the job that I want to do of the modeling faster. So in some sense, these are tools that you can take to your decision makers and be like, they'll be like, we can't ship this. And you'll be like, oh no, but here, we could just make it a little less forceful. Or no, look, here's an interesting technique for making it less frequent. So in that sense also, these are really good things for you to know and good conversations for you to be able to get into. All right, I hope none of you fell asleep, or if you did, you'll wake up and listen to it from the beginning, and I'll see you next time.